Sometimes it's not the model, but the data. There's a lot of sayings around this. Garbage in, garbage out. You can't make a silk purse out of a sow's ear. Just like us humans, neural networks learn from example, and if the examples aren't great, the model won't learn either. The other thing to consider is to have enough varied examples. Let's consider what it takes to teach a kid what a dog is. There are many different kinds of dogs, not just different breeds, but even within a breed there are many different variations. Size, color, hair, length, the size of the snout, the length of the tail. If I was an alien that came from a different planet, I might be surprised to learn that Chihuahuas and Great Danes are from the same species. At the same time, we should also be providing many different examples of what a dog isn't. Coyotes, foxes, and jackals are all closely related, but are technically not domesticated dogs. If we only proved one or two examples of what a dog is and what a dog isn't, our model won't be able to generalize its definition of a dog. Sure seems like a lot of work. Wouldn't it be great if we didn't have to do all of it? If you've ever spent time altering photos digitally, we're going to be using a lot of the same tools found in Photoshop or GIMP to expand our datasets. For instance, even though I've changed the hue in our marble photo, we can still tell that it's a marble. Many machine learning frameworks already have tools in them to alter photos. We're going to go over a few of the tricks available to us. These aren't tricks that will always work well in every situation. Depending on what we're training our model to do, we might end up confusing it instead. Let's say we're making a model to identify flowers. Color would likely be critical information, so changing the color like I did above would end up being unhelpful. Let's start with image flipping. In this case, we can imagine our photo is printed on a sheet of paper, and we're just flipping that sheet of paper over. Fair warning though, flipping an image dataset might not always be appropriate. Fun fact, with a few exceptions, most words in American Sign Language can be mirrored depending on whether you're right-handed or left-handed. So horizontal flipping is appropriate for our dataset. On the other hand, vertical flipping probably is not effective since people aren't usually upside down when signing. We can also think of the MNIST dataset. If we both vertically and horizontally flip our 6s, they'll look like 9s, unnecessarily confusing our model. A related tool is rotation. We can still imagine our piece of paper, but now we're rotating it. Is this one that's appropriate for American Sign Language? Within reason. Just checking in with myself, it's pretty difficult to get into the exact same position 100% of the time. But we might also expect a hand sign at 90 degrees would be pretty out of place. In fact, with many of these tools, it's easy to go too far. Let's take a look at zooming. If we think of our sheet of paper analogy, we can imagine we're bringing the sheet closer to our faces. Here, we have our marble, and we're zooming in on it more and more from left to right, top to bottom. For the first 2 or 3, yeah, we can tell that it's still a marble. But especially for the 4th one, we're starting to lose too much information to be able to properly recognize it. We usually only zoom into our pictures, because if we zoom out, we'll need some sort of padding around the edges to keep our picture the same number of pixels. When we zoom in, we can keep track of the pixels outside our field of view in order to do some shifting. Another word for this is translate. We're just going to move our image left to right, horizontal, or up and down, vertical. In the center here, we've zoomed in on our marble. Each of the surrounding pictures has the same zoom, but has been shifted either up, right, down, or left. All of these ways where we can warp an image in a physical dimension has an underlying concept called a homography. We can imagine we have a camera and an image, and depending on our camera's position and our image's position, we can project our image in 3-dimensional space. We can do all of this with some matrix multiplication. Pretty neat! There are other things besides physically moving our image. We can adjust the pixel values as well. Here, we have some examples of brightness. This is a great one to consider for real-world images, because unless the photos are professionally shot, it's unlikely that lighting will stay consistent. Just don't get too crazy with the brightness adjuster. If it's too dark or too bright, we won't be able to see the image. In the upcoming lab, we'll be working with colored images. Colored images are 3D objects, the third dimension now representing different color channels, like red, green, and blue. Each of these different channels has their own independent value. So for instance, if the red channel is 255, green is 0, and blue is 0, then the pixel value will be red. Red 125, green 0, and blue 255 result in a purplish color. There are non-color channels too, like alpha and RGBA, which represents transparency. Channel shifting takes the pixels in each of these channels and adds or subtracts a random amount. A closing thought before we move on to our next section. How many pictures did we get out of our original marble image? By my count, it's 39, including the cropped ones. This is an extremely powerful way to get more data. Pro tip: randomly sample the images coming out of our random image generator. If the images can't be interpreted by the human eyes, chances are the computer will have a tough time too. Okay, one last thought before moving on to the next lab, and that's model deployment. Our model expects a particular input dimension, but it's very possible that when we deploy our model for use in production, or the real world, the format of the data we get from users is different than the format we trained on. Also, Keras models typically assume training batches, meaning it learns on more than one image at a time. Let's say we get an image that we want to make a prediction on that's a different shape than our model trained on. We could resize the image to get the correct width and height. If our image is in color and our model trained on grayscale, there are tools to do the conversion. Another way is to take the average between the red, green, and blue channels. Finally, to turn it from a single image into a batch, we can add a new axis along the first dimension. That's just a fancy way of saying we're going to put a new pair of brackets on the outside of our image. Okay, that's enough theory for now. Let's get some practice in the lab.